Everyone, we're live. Welcome. Welcome to ML Real Talk. So put in the chat if you just joined, tell us where you're from, um, what's your background, what made you excited about today's conversation. Okay, so let's just get started. Um, Today, we're going to talk about 5 reasons why adapters are the future of fine tuning. Before we get to our topic, so all lines are muted, and if you have to leave early, today's session will be recorded and published on the Data Scientist Show. Submit your questions, participate in the polls, and if you want to try Predibase, you can go to pbase.ai /get started. All right. So my name is Daliana Liu. I used to be a senior data scientist at Predibase, and before that, I worked at Amazon, and I am the host of the Data Scientist Show. And today, joining me is Geoffrey Angus. Geoffrey is a team lead at Predibase. Geoffrey, do you want to tell us more about yourself?
Yeah, sure thing. Hello, everyone. I'm Jeff. I am the team lead for the ML team at Predibase. Prior to this, I was at Google Research, producing the image embeddings for Google Lens and Google Image Search. And prior to that, I was at Stanford doing medical imaging research with the Stanford Hospital.
Awesome. So, as you have been following the news around large language models, every model published is getting bigger and bigger. However, we think smaller LLMs are the future because fine tuning LLMs can be very expensive and it can also be slow. Today, we're going to talk about adapter based training, which is a game changer. It can enable fine tuning. At a very low cost and make it more efficient. So, what is adapter, Jeff?
Yeah, sure thing. So I'm going to quickly share screen here. Yeah, great question. So I'm going to leave this up while we just set the stage. An adapter, and this is not from a dictionary, I just made this up, is a small set of trained model weights that are produced during fine tuning. Yeah, and so what we're going to talk about today, there are going to be 5 reasons for which I have a few slides. But before we get into that, maybe we can just make sure that we have the right definitions in place.
Yeah. So, for the folks who are not familiar with fine tuning, maybe you could remind us what is fine tuning before we talk about adapters.
Sounds good. So fine tuning is a pretty fundamental concept in machine learning, though with the rise of models like GPT-4 and even the open source models like Mixtral and such, it is not as common now as it might have been in the past, like we're talking like 2018. But fine tuning is pretty straightforward. Essentially what it is showing your LLM new data and modifying its weights. So typically when you are using one of these generative AI models, what you do is you pass your prompt in through a set of model weights, and then that produces the output. Fine tuning is a step where you have some ground truth output that you want to try and coerce your model towards. And what happens is that is computed during a backwards pass. And so the output that is generated by your model is compared against your ground truth output. A loss is computed, and then a backward pass happens, which actually directly modifies the model itself in order to make it produce something closer to the output that you would have expected in the next time that you ask that similar input.
Mm-hmm. I'm just looking at the chat. Michael said audio restarting. Someone cannot hear. Okay, I think we're good.
Okay.
Um,
Oh yeah,
Great.
and sorry, just quickly, for the rest of the audience that has some experience, when we're considering fine tuning, a lot of times it's compared against something like RAG. And the differences are something along what you see in this slide. Ultimately, what RAG is modification to the prompt, and fine tuning is modification of the weights. And so, what happens in RAG is typically you have documents that are information about your use case. Let's say, data about the user. And what you can do with a RAG system is insert those snippets of information into your prompt before asking the model questions. But fine tuning is different insofar as it is an alteration of the weights that affect how the model thinks about prompts as opposed to the prompt itself.
Hmm. And can you give us a few examples on what type of applications we're using that's backed by RAG and what is used in like fine tuning?
Mm. Yeah, sure thing. So when I think about RAG applications, I do think mostly about the hello world of LLMs, which is the chat with your documents use case. So oftentimes when people talk about RAG systems, what they're talking about is a use case where you have, let's say, documentation about a repository, like let's say pandas, and you've converted that set of documents or that documentation into a set of chunks, and then you have a retrieval system that compares your prompt to possibly relevant snippets of documentation and then dynamically inserts it into the prompt so that your LLM has the context to make the answer. So for example, if I say, how do I read in a data frame from a CSV file? And I say that to my large language model, the retrieval service will look at that prompt, compare that to the documentation in pandas, find the relevant chunk of code, put that in the prompt so that the LLM, instead of having to think and look into its weights to come up with the answer, can do a much more simplified task, which is reading comprehension. It essentially just, the prompt at that point is, how do I read in CSVs using pandas? And then the rest of the prompt says something like, here is the relevant context. PD.read CSV is how you read CSVs in pandas. And then the
Hmm.
LLM can look at that and say, oh, this is what you want. And so it's a little bit, it's very simple in that way, and very useful though, insofar as it's very straightforward to conceptualize. The one thing I will say about that use case is that it doesn't do things that sometimes fine tuning can be a lot better at. And one way that many have thought about things, and this is changing over time, is that
Hmm.
RAG is for facts, so fact retrieval, and that fine tuning is for form. And so, an
Yeah.
example of where fine tuning could be really useful would be where you want to produce JSON outputs using your LLM, and oftentimes when you ask ChatGPT, produce me a JSON for this bit of data, it'll say something like, sure, happy to do that. Like, here's a JSON for you. And that sure, happy to do that is super annoying, especially if you have a program that is trying to parse the JSON. And fine
Hmm.
tuning is a way to alter the model's behavior, is another way to think about it, so that it doesn't add all of that preamble and just produces the JSON you're looking for.
Yeah. So fine tuning works well for standardized tasks specific for a business use case. And a lot of companies are starting to fine tuning their own LLMs. But what are the shortcomings of fine tunings? We previously talked about it could be slow, could be expensive. Can you tell us more about it?
Yeah. I actually have a slide for that as well. So here we have that figure that I showed you earlier, right? Showing your LLM new data and altering its weights. What happens is during the forward pass, yeah, you're computing tokens for a given input. But during the backwards pass, actually a ton of stuff happens behind the scenes that makes fine tuning all of the weights directly really, really hard. So what I mean to say is that full fine tuning, which is where you adjust all of the model weights directly, is extremely slow. Uh, the reason why is because for the math people out there, you're computing gradients across all of the weights in order to minimize the loss between your ground truth output and the model's generated output. It's extremely memory intensive because not only are you storing the gradients, you're also storing optimizer states. So for example, the Atom optimizer stores these beta 1 and beta 2 parameters for each weight, so that doubles the amount of memory required just from the Atom optimizer state memory by itself. And then this all equates to it being much more expensive to train. So if you only require, an NVIDIA A10G to serve your model, you might require 4 A10Gs in order to train the model. So overall, full fine tuning, while it is super useful to fine tune and get these structured outputs and modify model behavior in the way that you see fit for your use case, it can also be quite burdensome, and a completely different infrastructure requires a different set of infrastructure considerations than serving the model.
Mm-hmm. And so how can we use adapters to improve the process of fine tuning then?
Yes. So when it comes to adapters, when I consider the difference between full fine tuning and adapters, it really comes down to the fact that adapters, so low rank adapters in specifically these like LoRa adapters,
Mm-hmm.
the difference is that what we do is we actually freeze the LLM's original weights. So you can see here that W is still here, but actually W is untouched in the backward pass. And we surgically insert new weights. They're a low rank decomposition matrices, A and B, that are able to capture a lot of the same gains of full fine tuning, but with much less memory and computation requirements.
Hmm. And for folks who are not really familiar with LoRa, maybe you can just high level let us know what is LoRa.
Mm-hmm. Yeah, so I'll go a little bit more into detail as I talk about the 5 reasons why something like
Mm-hmm.
LoRa is what you want for your use case. But at a high
Yeah.
level, essentially, LoRa is uh, really simple to apply. It it is something that allows you to achieve performance parity with your original set of weights.
Mm-hmm.
And like I said, it allows you to reap the performance benefits of full fine tuning without actually doing full fine tuning.
Got it. Okay, so I think we have provided a lot of context for our discussion. Are you ready to talk about the 5 reasons why adapters are the futures of LLMs?
Yeah, definitely excited to do that. I'll try and keep it super, high level, but if you have questions, definitely ask them in the chat. And we'll see if we can get to them. Cool. So yeah, I guess we'll just get right into it. So reason number 1, first and foremost, I think that probably a lot of you are thinking to yourself, okay, full fine tuning versus LoRa. If LoRa is applying, is as good as it says it is, and allows you to get these memory overheads, are there trade-offs? And the answer that I'll give you immediately is that first and foremost, the reason why you want to do adapter-based fine tuning is that for the most part, you actually don't see trade-offs in model performance. So while you are training less parameters, you are still capturing a lot of the same value that you would get in full fine tuning. So here are 2 results from the table. And if you look in the bottom right of the slides, you can see the archive link, which we'll also provide to you maybe in the description. But what we have here are Roberta Large. So this paper is from 2021. We have here is Roberta Large, full fine-tuned, and Roberta Large LoRa. And then we have dBERTA XXL, full fine-tuned, versus dBERTA XXL LoRa. And you'll see that on, let's see, 8 academic benchmarks, you actually see a back and forth between performance differences between full fine-tuning and LoRa. So for a task like SST2, which is something like sentiment analysis, you see that full fine-tune may perform better. But for something like an NLI task, which is talking about entailment and otherwise, actually LoRa training is better. And on average, for whatever reason, this might just be noise in this paper, but on average, if you look at the far right column, LoRa performance is actually better than full fine tuning, which is a little surprising, but just goes to show that it's really pretty powerful stuff.
Yeah. So this is the first one, performance. There's not much trade-offs. And what is the next one?
Yeah, so you may notice this big black box. The reason why is because the reason two is that it is, and three is that it's extremely efficient. So I've combined them here so that we can just sort of talk about it. But reason two is that the memory footprint is extremely low. And reason three is a corollary of reason two, which is that this leads to faster fine tuning jobs. So you see this graph, you see the performance, you think to yourself, how much could the savings really be if we're getting good performance like this? And the savings are quite staggering. Roberta Large, full fine-tuned, is training in excess of 350 million parameters. dBERTA XXL is training in excess of one. What is this number? 1.5 billion parameters, I guess is what that would be. And the LoRa trainable parameters are 0.2% for Roberta and 0.3% for dBERTA. And of these total trainable parameters, leaving you with a really large performance gain and therefore a faster fine tuning.
Mhm.
So yeah, good.
Yeah, go ahead.
Oh yeah. So one thing that's nice is that this leads to a lot of optimizations under the hood that one can make. But before I get into that, maybe I'll explain a little bit about how this is possible.
Mhm.
Um, so what I'll say is that the secret lies in the fact that A and B are what I said were rank decomposition matrices, and that may sound very mathy, but essentially what it is that you have two matrices which have very small, very narrow or very wide, depending on which orientation you're looking at, shapes on one side of the matrix, which allows you to save on parameters. So if you look at W, which is what we would train in full fine tuning, it has a shape, let's say 1024 by 1024. And so the trainable count for that is 1024 squared, which is in excess of 1 million parameters. But if you look on the A and B side, B might have a shape like 1024 by 8, and A might have a shape of 8 by 1024. So the total parameters that you're actually training there are 8,000 plus 8,000 roughly, which is 16,000 parameters. And that is less than 1% of a million. And so you're getting a lot of the gains from the fact that these matrices are so narrow and that W is frozen, so you don't have to store any optimizer states from that.
Mhm. So for the folks who are, still following the math here, can you give us maybe a high level kind of comparison, based on the W and then the AB matrix based on basically, yeah.
Yeah, sure thing. So the main thing I'll say here is that the reason why this works is very mathy, but I'll break it down insofar as the W matrix allows you to be very expressive about what your model is doing.
Mm-hmm.
And what the researchers found was that when you do full fine tuning, you don't actually have to change W that much. So you're doing full fine tuning, but the final result of a trained W doesn't look very different than the first W. In fact, you can represent it in 16,000 parameters, that change. So what the researchers did when they created LoRa was they designed a way to affect W in a very lightweight way. And that's why you have a lot of the performance gains, because this is intentionally designed to capture much of the variance that's created during training, but is done so in a very simple and sort of light touch way, as opposed to what full fine tuning is, which is very heavy.
Got it. So say even if you do a full fine tuning and you might not change all the parameters to achieve the results you want to have, however, you still use all the resources you have to use to, learn all the like over a million parameters.
Exactly. Yeah. You spend all of this time just to get a W that is approximately similar to your initial W. And that variance is captured with much less parameters than you would otherwise train in full fine tuning.
Yeah, got it.
So one thing that I wanted to make sure that I covered is what the where the efficiency gains come from. So it's true that you get this dynamic. So I'm saying that you train less parameters, but what does that mean? Is one question that I might be getting in the chat. And what is that? What is the downstream effect of less trainable parameters?
Yeah.
The effect of having less trainable parameters actually comes down to the optimizer that you've chosen to use. So if you're using what is an industry standard, something like Atom or Atom W, like I said earlier, you're storing optimizer state for every single parameter in your network that is being trained. So if you have Llama 7 billion, you are storing a copy of 7 billion parameters to keep track of the momentum of the optimizer and a second order momentum parameter for each of those weights. So you have two copies of your model in memory just for every single trainable parameter. And what this does is it virtually eliminates those copies because now you're training, 0.2% of the weights. And so that optimizer state is not even something you need to consider when you're doing training anymore. So now you've gone from one A10G to essentially one A10G again, as opposed to one A10G to four A10Gs for training. The other thing is, if any of you have trained models, you'll know that oftentimes one of the training bottlenecks actually comes from the checkpointing step, especially for these large language models, because you have this I/O step that goes from GPU memory to CPU memory to disk. And when
Hmm.
you are training models like Llama 70 billion, that can actually take a really long time. And I remember when I was at Google, when we were doing these large training jobs, we actually had a separate job that would listen for checkpoints and write
Yeah.
checkpoints asynchronously because it would take such a long time to offload these weights to disk. So with something like this, where you're only training 0.2% of the weights, like I was saying, that step is near instantaneous because you've gone from moving tens of gigabytes of memory around back and forth, or I guess you're not leaving GPU memory, but we're moving that memory to disk to tens of megabytes of memory moving to disk. And so checkpoints now become easier to store, easier to manage. If you're doing experiment tracking, now you can checkpoint much more frequently. Um,
Hmm.
and so you reap a lot of benefits from this low memory footprint. And then the final thing I wanted to cover was that when I say faster fine tuning jobs, of course, part of that is the fact that you're not that there's I/O considerations and the fact that you are not necessarily doing this training across all parameters. But another thing is that this lower memory footprint is allows you to increase your batch size a ton. So if you do happen to have 4A10Gs, you can quadruple your batch size quite easily, maybe even more than that. And then also, the researchers said by having trainable parameters in the paper, they mentioned that there's a 25% training throughput increase. But in my opinion, I think a lot of the gains come from the fact that you're able to quadruple or octuple your batch size if you had the right compute requirements to begin with.
Hmm.
Cool. So yeah, so those are reasons 2 and 3. I'm going to move on now to reason 4, which is that we have seen that adapters enable multi-model serving. And what I mean by this is a little bit of a case study. So if you are just getting started on your privately hosted open source LLM journey and graduating from OpenAI, you may have one model deployed, maybe something like Mixtral, and you haven't fine-tuned it. So you're paying, 62 cents per million tokens or something, 31 cents per million tokens. But over time, as your business scales, you might find that you need to fine tune for different use cases. So if you're a customer service app, maybe you want to fine tune to do sentiment analysis, or maybe you want to fine tune to write customer service emails particularly well, or maybe you want to fine tune to do summaries of customer issues so that your customer service workers are able to better triage problems and to be able to do that more efficiently. If you're in this position where you find yourself with multiple fine-tuned models, If you're fully fine-tuning models, you're going to need a deployment for each of those fine-tuned models, and that quickly becomes untenable. So in this graph, if you have 2 deployed models, maybe that's 62 cents per million tokens. But once you get to 128 deployed models, that's looking like $40 per million tokens, which is an insane number. Um, and part of the difficulty there also is that maybe initially 100% of your traffic was going to 1 or 2 deployments. But now, if you're in the scaled case where you have 128 deployments, your traffic may be split 128 times. So even if you have these models deployed and they're being hosted 100% of the time, 24/7 uptime, you may not even be getting the throughput to justify the cost of hosting these models 24/7. Fortunately, with something like adapters and with something like our open source framework LoRAX, you can actually host all of these models, provided that they're fine-tuned against the same base model, on top of a single deployment. So what I mean by that is, like I said, your base model might be tens of gigabytes, but the adapters may be tens of megabytes. And so moving adapters from CPU memory to GPU memory takes milliseconds, and moving them off also takes milliseconds. And you can imagine a case where you are able to hot swap adapters into that same model and keep that 100% of your request traffic going to the single deployment, as opposed to splitting it across hundreds of dedicated deployments.
So you have the fine-tuned base model, and then basically for different use case, you have a different type of adapter, and that can kind of reduce the cost of serving.
Exactly. Yeah. So you may have a base model that is useful for general tasks. So maybe something like ChatGPT. But if you have very specific business use cases that require a little bit more structure or a slight modification to your model's behavior, it is much more beneficial to deploy using adapters than it is to deploy with full fine tuning, because of the gains you get from reducing your dedicated deployments from dozens to 1.
Yeah.
Cool. So I'm happy to get into a little bit more detail here about how this works, but I'm curious if you have any questions so far, or if you think we should be moving on just based on time.
Yeah, I think we can continue.
Cool. So yeah, and we'll definitely be happy to answer follow-up questions in the chat, or feel free to ping me on LinkedIn or otherwise. The final reason that I want to get to then is that adapters are only getting better. So the first few reasons are really fundamental concepts that have to do with adapters and why they're better than fine tuning. The fourth reason is really a tactical reason for cost. But this fifth reason is a little bit more speculative and should be taken with a slight grain of salt, insofar as this is all work that is ongoing. The fifth reason is, so fifth reason, point 1, is that coming soon, LoRAX will be a place for you to have one deployment for all of your LLM use cases. So LoRAX today already supports modifying the behavior of LLM base model for generative tasks. And what I mean by that is what I said in reason 4, so swapping in different behaviors for your LLM base model. But in the pipeline as well is the ability to serve embedder models for your RAG systems using that same LLM base model. So there was the current leader in the METB massive embeddings, or massive text embeddings benchmark on Hugging Face, is a model that comes from Salesforce, and it is an Mistral 7B instruct model that has been fine-tuned for the embedding task. And so what that means is that you can actually use LLMs as your embedder to get really, really strong results. And if you can train it, you can adapt it. And text embedders here are something in the pipeline that you can imagine using that same LLM-based model you already have deployed for retrieval, RAG use cases as well. The other thing is that you can also deploy text classification. So sometimes this is nice because you really want to constrain the output of your generative model to just a yes, no, or to some classes. Maybe you want to do this for explainability reasons, like you want to have the probability like 0.6% chance that it's negative, 0.3% chance that it's uh, fraud or something along those lines. And LoRaX will be supporting that as well very soon. And then finally, we've seen a lot of recent research in ways to fine tune your model in order to get latency speedups, like Medusa. So here you have a case where maybe your LLM base model produces tokens at 20 tokens per second. But with something like Medusa, which does decoding through multiple heads, so each of the heads are generating different tokens at different time steps, you can actually fine tune a model like this to get your tokens per second up to 60 tokens per second, for example. And this, if like I said, if you can train it, you can adapt it. And this is also something that you can apply as an adapter in order to really boost your numbers. And with something like LoRaX, all four of these use cases are servable from a single deployment. And therefore, you may have a RAG system that requires taking your query, embedding it, retrieving relevant documents, and then classifying it, determining whether it's fraud or not fraud, and then generating an email response for your user, maybe applying something like Medusa so that they know that their request has been seen and is being handled. And all of that can happen in one sort of set of requests that all go to the same place. So I'm very excited about this possibility for adapters, and it's something that we're actively building.
Yeah, definitely want to see how we can actually use a adapter later. Maybe you can give us a demo, and then I see some questions. We can get to them later. But before we go there, I'm curious, what are some best practices when someone wants to use adapters, and have you observed some like common mistakes?
Mm. Yeah, sure. So I think that the best practices for adapters are still being hashed out. There, like I said, it's an active area of research, and I think that one of the main things to consider is whether or not you have the right amount of data to train one of these models. I think that one of the questions we get a lot at Predibase is, how do I know if I have enough data for fine tuning? And that question still applies when you are considering adapters. And it's very much heuristic and something that you develop an intuition for over time, but hundreds of data points is typically sufficient for training an adapter. And the other thing that I'll point out is that oftentimes synthetic data, which is another trend in LLMs, is something that you can apply to train a good adapter. So what I mean to say is, if you do find that GPT-4 is useful in a lot of your cases, but you maybe find that it's too expensive, or maybe you have some privacy constraint that you're ultimately hoping to fulfill down the stream. Um, what you can actually do is do request response logging to make sure that you capture all of that information so that you can then apply that to a fine-tuning job for adapters. So in terms of best practices, I think that oftentimes what you should be doing is thinking about, how can I bootstrap the data required to do fine-tuning? And also, I think one thing that I would consider is, if you do plan on using adapters, consider standardizing around a single base model, because if you have multiple adapters across multiple base models, then they become less effective, right? Like if you have
Yeah,
five
it's hard
adapters
to compare.
yeah, it's hard to compare, and you don't get the benefits of something like
Mhm.
LoRaX, where you're just recycling the same base model over and over again.
Right. Um, so do you have any examples you want to show us? How do you train an adapter yourself?
Sure. Yeah, so I can get right into that. So actually, we just did this. We
Mm.
just made a release called LoRaLand, and this will take me as a segue for everybody watching.
Sounds like a fun playground.
It is a fun playground. And essentially what it is we did everything that we said here. We thought, it's important to put your money where your mouth is and not just tell everybody adapters are great, but to actually try it out for ourselves. And
Mhm.
we learned a lot along the way, which I can describe. But essentially, LoRaLand at a high level is 25 plus small fine-tuned Mistral 7B adapters that are on par or outperform GPT-4. All of them on our side are served on a single GPU with auto scaling if we get a lot of demand, which we see a lot of people putting in requests. So we're happy about that. And what I'll actually do for my demo is show off LoRaland a little bit for anybody who wants to see it. And then I'll go behind the scenes and show you guys how one could train an adapter like the ones we use in LoRaland through Predibase, and by extension through Ludwig, which is our open source offering for LLM fine-tuning. So yeah, here's my screen. Here is LoRaland. And for those who have not logged on to this before, essentially what we do is we break our adapters down by category. And so here, you can select any category. There's the academic benchmarks like the MNLI and QNLI, which were in the LoRa paper that I was describing earlier. But what I want to do is show you a JSON structured output generation use case. And here what we have is a use case where we are comparing the fine-tuned model response. So this is the adapter-based fine-tuning response, and then the base model response, which is just basic Mistral 7B instruct. So here is the prompt that was used to train the model. Very simple. I gave it a little bit of a few shot flair just to make it a little bit more sample efficient. But essentially, it just tells the model to look at a sentence and then output JSON that maps to the entities in the sentence. So if I run this, what I see is that both models actually produce valid JSON. So that's a good thing. But you'll see that our fine-tuned model was able to place. Oh yeah, sorry. Did I show you guys the prompt yet? Here's the actual input. So the input is, by the close, Yorkshire had turned that into a 37-run advantage, but off spinner such had scuttled their hopes. And what we see is that our adapter was able to place such in the person category, whereas the base model was put it in the miscellaneous category. So I guess it recognized that there were some adjectives here, but it wasn't able to realize it was a person in the base model case. But our fine-tuned model, which was trained on data that looks much like this, was able to place it correctly.
Cool. So the fine-tune model here use the adapter, and the base model is just it wasn't fine-tuned at all.
Exactly. And so when we consider what that looks like for LoRaX, so like I said, single GPU, and that includes the base model response. So LoRaX is, you've got your Mistral 7B instruct model loaded into an A10G, let's say. And to make this query, what it did was it loaded in the adapter, produced a response, and then, actually there's a little bit of CUDA kernel magic happening, but you can imagine that another way to imagine it, maybe simpler, would be that it took out the adapter and then ran the base model response. So there are you're able to use that one GPU to get both of these responses, which I think is very cool.
Yeah. And can you take us behind the scenes, and how does the training process look like?
Yeah, sure thing. So first, I'll show you the data, and then I'll show you the Python script, and then I'll end by showing you what the trained model looks like in Predibase. So this is what the data actually looks like. This is the ConNLP dataset, or ConLLPP, or I guess plus dataset. And this is the data that I trained the model on. So it was actually a lot of rows for this one. This was 20,000 rows, but you can get away with much fewer. This was just the size of the data set that we pulled down.
Can you give us an overview of what does this data set do? What is it about?
Yeah, sure thing. So that's what this preview here is, which is that the input column, so what we're actually going to, maybe zooming out actually. The data set is, like I was talking about, it takes in a natural language sentence. That one's actually a really bad sentence, but something like this: the foreign ministries, blah, 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 told blah, blah, blah in an interview. And what it does is it maps the entities in that to a JSON object that splits it between person, organization, location, and miscellaneous. So for this example, the people were Tang, the organization that was mentioned were Shen and Reuters Television. The locations mentioned were Taiwan and Beijing. So that's what the data set looks like. And what we essentially do in order to fine tune is we set up a prompt template that takes in the input and then compute loss and compute gradients against this ground truth output. Oh, okay. Well, my Jupyter notebook seems to have died. But Essentially, what we do is, in order to train this model through something like Predibase, which is a fine-tuning platform for LLMs, is all we have to do really is connect to our SDK and then pick the deployment. So here, our base model is going to be Mistral 7B, which is going to be what we fine-tune the model against. And then, whoa, okay. What we do actually is we fine-tune the model with a very simple, 5 lines of code. It could be 1 line of code if I didn't want it to be as organized. Prompt or function call, which takes in the prompt template, which is what I showed you in LoRaland, and the target. So this is the target column output, like I had here.
Mm-hmm.
And then the data set, which was conllpp. So what this is doing behind the scenes is it applies this prompt template to the input column per row, so that that's what the model sees per row, and then puts the model onto some amount of compute. So here I think we use a 80 gigabyte A100, and then we compute loss against the output column per row in order to fine tune the model. And it's not shown here, but what we're doing is we're actually applying adapter-based fine-tuning out of the box so that you get those memory savings without having to make much consideration at all.
Mm-hmm. So this is your own Jupyter notebook, right? It's run locally.
Yeah, exactly.
And so basically you can do this with the SDK provided by the Predibase library, or you can also do the same thing in Predibase.
Exactly. Yeah. So you can do it through the UI or through the SDK. Figuring that most of the audience is data science or software engineers, the SDK is what we see actually is our most common entry point for our product. Sorry, I'm actually just going to restart this Jupyter notebook because it keeps popping up the thing.
Yeah, and while you're restarting, if you're in this live webinar, you can try Predibase, click on the button on the lower left side, you get 25 free credits.
Yeah, that's right. Cool. So got my got the notebook back up, and what I wanted to say quickly was that Predibase also manages the infra for you. So what we were talking about LoRAX and is actually something that we serve out of the box. So after this model is trained, we can actually grab the adapter straight from here and then apply that to this deployment. And so here, what we can say is llm.withAdapter, this model that was fine-tuned. And what that will do is allow us to run inference against that deployment using that adapter and get you back the response that you require. And so I think right now it's doing a little bit of a cold start, so it will reload that GPU. But in the meantime, while that happens, we can take a look at what you can find in the UI. Like I said, you can train models from the UI, but this will also automatically populate when you run the SDK training job. And so what we'll see here is what it took to actually train this model. It ended up training for 2 hours. We use a single A100. And here's the fully rendered config of what we did in order to do the adapter-based fine-tuning. And this is a Ludwig config, which is our open source training engine that we use for LLM fine-tuning. And you can see here that the adapter type was LoRa and that we trained against Mistral. Actually, this one was Mistral base as opposed to Mistral instruct. But the point is that Predibase makes it super easy to do fine-tuning, and it also makes it super easy to do adapter-based serving. And you can see here that the generate call succeeded, with MLK being placed in the person category and Atlanta being placed in the location category.
Oh, cool. So the config file you just showed us, it looks like it's like a large config file. So for someone who just got started in fine tuning and they don't know what to change, what to tune, do we have a template kind of give users some guidance, kind of when to do what?
Yeah, so the nice thing about Predibase is that a lot of the guidance is baked into the way we design our default configs. And so, as you saw, this is how the sausage gets made. We do gradient checkpointing, gradient accumulation in order to overcome the fact that our batch size is relatively low. We do 4-bit quantization. We do all of this stuff to make the experience as easy as these 3 lines of code or 5 lines of code.
Mhm.
But they're all also very much configurable from this location. So if you were to do something like config equals, I think it's like get available configs or maybe get default config, and then you can actually edit this uh, in this format in order to set these values yourself. So, and then you would just go, config equals config or something along those lines. So the point is that it's we have the philosophy of revealed complexity at Predibase, where it's simple to start, but fully customizable to your use case. If you are a pro, go ahead, let it rip. Feel free to test our system. But if you're just getting started, you want to deploy open source LLMs with little thought to how the infra is managed and how the models are trained. You just want it to work. Predibase provides that just works experience and gives you the option of graduating from OpenAI and owning your models and your serving costs without much difficulty at all.
Awesome. Last question before we get to the Q&A part. So say if I fine tune a model and I'm not super happy with the results, what are some ways for me to debug? What are some other knobs I can turn?
Yeah, sure thing. So I think probably the best thing to do is to put on your data science hat for all the data science viewers out there and take a look at the learning curve and just make sure that it all looks as you would expect. So this is a learning curve that it looks like it's out of a dream because of how like canonical it actually is, which is that you see the training loss go down and the test loss sort of staying where the training loss approximately is throughout training, but you'll often see different shapes, and those allude to different remedies for something along those lines. So often, what you might see is that the training loss will go down, but the test loss will go up, and in that case, you'll have a case where your LLM has memorized your training set and doesn't know how to move past the examples that it has memorized, and so you might see that it does really well on examples it has seen, but when you ask it to look at new sentences that it hasn't seen before, it might do really poorly. In which case, you might want to apply regularization like dropout or weight decay, or realistically, you may want to decrease the overall expressiveness of your model. So if you're using Llama 70 billion and it's memorizing your training set and nothing else, maybe it's too good of a model, maybe it's too deep of a network. You can try simplifying to reduce the expressivity of your model, and maybe that the simplicity captured by something like Llama 7 billion does better for generalization than a model that might be bigger.
Great. Okay, let's get to some questions. So I think you have already answered a lot of questions during your presentation. So here, I think Dan asked interesting question. Can adapters tuned from one model, for example, Llama 7B, be used by another model, for example, Mistral 7B?
Mm. Yeah. So that, yeah, I did. I think I alluded to an answer to this, but to make sure that I got the point across, these adapters are not necessarily interchangeable between base models. That's because of the dependence on W. So A and B sum into W, actually, if you look at the actual formulas. And what that means is if W is different because it's a Llama 7 billion model or Mixtral model, A and B will no longer be useful to the model. And so you will want to retrain that, but provided that you have the data, the training job should take less than 2 hours, less than 2 to 3 hours, because of the size of the adapters is so small relative to the base model.
Yeah. So Kyle said, I would love to see a Predibase guide on creating your own LoRa adapter. He also asked, when is text embedding classifier and multi-head decoder support expected to go live in LoRAX?
Nice. Okay. Good question. Yeah, so in terms of Predibase guide to train your own adapters, that actually will follow the launch of LoRaland. We're putting together an archive paper with just like a dump of all of the findings that we had, a little bit more fine-grained metrics into why these models outperform GPT-4, the choices that we decided to make, and why, and also some preview into what models didn't work that didn't outperform GPT-4, so that you can get a better sense of when to train adapters and when to maybe not. Um, so a guide is coming out soon in the form of that archive paper, but also I think that this is, just the beginning of our adapter-based fine-tuning uh, roadmap, and a lot of the continued content and the educational material will come out in the coming months. So actually, there's another blog post that shows how Ludwig and LoRAX can work together, and that can serve as a guide, at least at the notebook level, on how you can functionally train an adapter yourself. With respect to when text embeddings, text classification, and look-ahead decoding will be landed in LoRAX, these are on our roadmap for the next, I want to say, 4 to 6 weeks. It'll be live in production. So, buckle your seatbelts. It's a lot of stuff for us to work on, but I think that definitely the open source community will benefit from it sooner, insofar as LoRaX and Ludwig are our engines for running Predibase. And so a lot of this stuff has to land in the open source first before it makes its way into production. So just keep an eye out on the PRs, and we'll definitely notify people on the LoRaX Discord and also in all of our social media channels.
Yeah, you can follow Predibase's LinkedIn and join the Discord channel. Ludwig also has a Slack channel. Okay, so Paul Olivier asked, what is the impact on GPU throughput of serving multiple adapters on the same model at the same time? Are there any gains to consider from the fact that they share the same base model?
Oh yeah. Oh yeah. So we're gonna have to go off script here. I just want to show you our blog because we have those results. Let me see if I can find it quickly. Predibase blog LoRaX. So let's see, is it in this one? Yeah, okay, here. So here is a result that shows how performance degrades as you serve more fine-tuned models. And the idea here is that there is a break-even threshold on this dotted silver line down here is sort of when the break-even threshold. It's a little bit of a complex graph, but the idea here is that you're going to get some throughput when you have dedicated deployments, right? So if you have 25 dedicated deployments, because you have 25 fine-tuned models that are all in their own GPUs, you're going to get some amount of throughput. But you're also going to get some amount of, or actually, yeah, you're going to get some amount of throughput. And this break-even point is how much throughput you need to be getting in order to justify the use of something like LoRaX. And so maybe that's not as important to your question. Actually, what's important to see here is that the throughput for LoRaX like very much sublinearly decays with the number of fine-tuned models that you're deploying. So if you've deployed one fine-tuned model, it's like I think 1100 tokens per second using LoRaX. But if you've deployed 125, you're still going to see 1034 tokens per second throughput through this deployment. And the reason why is because we actually have a CUDA kernel that I'll attribute to Punica. So there's a paper called Punica by Lekun Chen. And he, in this paper, describes a CUDA kernel that allows you to fuse the operations for adapter forward passes in a way that allows you to put them into a single batch. So a lot of the gains from LoRaX are actually from the fact that we're able to batch your requests. So if you have, a huge spike of requests coming in, we're actually going to process those all together as opposed to one at a time. And the CUDA kernel allows us to do multiple batches or multiple adapters in a single batch. And that's why you see this sublinear throughput degradation, which I think is super cool and definitely not something you see a lot in the open source. And here's also the latency graph, which shows that latency does not degrade by more than it looks like a couple of thousandths of a second even at hundreds of adapters at that point.
Awesome. So here are a few questions in recent messages. Are you able to see the chat, Jeff? I wonder if you
Oh yeah.
want to pick a few to answer, say, starting from Lydia's question, Mahiter, Dan, Jared.
Oh yeah, nice. Okay, cool. Yeah, let's get so here there's a Jadari. Our adapter is supported by MOE architecture. So that's actually one that I skipped for the sake of the demo, which is that reason number 5, which is that they're only getting better, is that we have something like LoRaland, and one of the pieces of constructive criticism we've gotten from the community, or maybe not even criticism, but like pieces of feedback, something that very people are really excited
Yeah.
about, is the fact that we have all of these adapters, but one of the main pain points that you can imagine is that you have to select which adapter you want ahead of time, which for
Mm.
some use cases defeats the purpose of having the adapter, because maybe you want it to be a dynamic thing. And there are actually 3 pieces of literature out there that are starting to explore MOE style dynamic routing between adapters in order to reap the benefits of specialized fine tuning with the generality of something like a GPT-4. And so what I mean by that is, okay, maybe this AB is for customer segment 1, this AB is for customer segment 2, segment 3, segment 4. What you may be able to apply in the near future through something like XLoRa or Fat Goose, I think MoLoRa was a slightly different thing, but is a router that you can train in order to either select or do a weighted sum of adapters that were trained either in the past or concurrently with the router. And what that means is that the lines between mixture of experts and adapters starts to get really blurry, and that's something we're super excited about. It's definitely on the speculative side because one thing that we've seen a lot of questions about is, oh, what if I wanted to train this route, or what if I didn't want to train a router? What if I just wanted to have each of these adapters be routed sort of in this like automatic way, and I can just sort of n+1 it every single time without having to change anything about LoRaX? Um, that's something that people have not solved yet. It's something that we're thinking about a lot. So if you have thoughts, definitely feel free to message me. But yeah, definitely something there.
Great. So do you want to answer another questions before we wrap up, or you want to get to the last slide?
Yeah, let me see what other questions we've got. Inference in a multimodal. Yeah. So, yeah. Lydia asked about during inference in a multimodal serving configuration, since you rely on one base model, there's going to be some queuing. That's another way to phrase the question that I had responded to earlier. If I understand correctly, there is no queuing outside of basic request queuing because of the CUDA kernel that is applied in this graph. It's very much just a global queue. The first iteration actually of LoRaX, which was some of the first commits in the repository are my own. And before we had applied the Punica framework, we were doing some crazy event multi-threaded queuing thing to get each adapter loaded and unloaded. But we did away with that in the, I think 0.2 or 0.3, which made it possible to do it without anything more than a global queue. In terms of the multimodal aspect of it, I just assumed this was multi-adapter, but if it were multimodal, like image and text, that sort of thing, I actually think that this is not something that LoRaX supports today. But if we were to go into the direction of vision transformers and other like image-based use cases, I think that it would have to rely on the pre-processing step that is part of LoRaX. I think commonly you see images tokenized into patches and treated the same as text, in which case, yeah, it reduces to the same problem that we had prior, which is that we're doing tokenization and multi-adapter serving. So you wouldn't need anything for a global queue, even if you did have a multimodal serving configuration as well.
Great. So today we talked about 5 reasons and also a lot of other things we covered. Before we wrap up, can you maybe give us a recap? What are something you really want us to remember to take away?
Yeah, sure thing. So actually, let me. I think we need this slide now. Um, Thanks everybody for attending the webinar. In summary, the 5 reasons why you should use adapters is that they work just as well as full fine tuning. They train 10,000 times less parameters. You are getting huge increases in throughput. You're not losing anything in terms of serving. If in fact, you're probably gaining, if you are at scale, you're gaining 10 to 100x in terms of your savings on dedicated deployments. And the 5th reason is because there are a lot of smart people out there working on this right now to make it even better. And as the line between adapters and mixture of experts gets even blurrier, I think that we're in a brave new world. And I encourage you to start learning about it.
Cool. What are something you want us to remember? Can you remind us the 5 things or the top 3 of the 5?
Oh, yeah. So those were the 5 things. The top 3 I would say is actually maybe just like the candid one-line summary is unless you really need to, you probably don't need to fine tune a full model.
Yeah.
Just try using something like LoRA instead.
Cool. Thank you so much, Jeff, for a great presentation. And thank you all for joining, asking questions. And look forward to the next one. And don't forget to sign up and try it on your own. That's the best way to learn.
Awesome. Sounds good. Thanks all.
Thank you.